Hi everyone, this is Dr. Athens and I wanted to run through the example problems here on our website under the instructor notes. This is stoichiometry with a chemical reaction equation, and the basic steps that we're going to do is you have to have a balanced chemical reaction equation to begin. You will, if not provided with moles at the outset, have to first get to moles because you can only relate two compounds within a chemical equation through moles. We do so by looking at the coefficients of the reaction equation, and we create a ratio to say two of these combined with one of those, and that's how we cross over to talk about the other compound and do some calculations. And then finally, if we're asked for grams, for instance, we'll have to convert from moles to grams of the final compound. So this is best learned by practice. So I'm giving you an example problem of moles to moles. These are actually pretty easy. Here's a reaction equation. This is called ammonia, NH3, to hydrogen gas and nitrogen gas, but we notice that it's not balanced. So the first thing I'm going to do is balance this. I need to put a 3 here and a 2 here, and then this is balanced. And if I have 5 moles of this, what I'm saying with this coefficient bridge is that I just look in the front of these, the coefficients, and that's what I relate. So I see that 5 of those will make 3 halves as many. 3 halves relationship between the hydrogen and the NH3, so I would get 7.5 moles of hydrogen. Moles to moles is easy. All you do is apply the coefficient bridge. Now the next example is with grams, and now this is more work because every atom has a different mass, so we have to get to a common base of moles to proceed to do the coefficient bridge. So let's balance this once again. We notice that this equation is not balanced, so a 2 there and a 3 there will do it. Now we have 5 grams. So the first thing I do is I get to moles. So I'm going to do that by dividing by the molar mass of 17 grams per mole. And when I do that, I'm going to find that this is 0.294. That's how many moles of NH3 I have. How many grams of H2 are produced? Well, first I'm going to do the 3 to 2 relationships. 3 moles of H2 are produced for every 2 moles of NH3. And then I have to get to grams, so I use the fact that there are 2 grams of H2 in 1 mole of H2. That's based on the periodic table. And when you do that and multiply it out, it would be 0.294, that's a point, times 3 halves. My mouse isn't cooperating. I'd get 0.88 grams of H2. Okay? Just to recap, if you're given grams, get to moles. I divide it by the molar mass of NH3, 14 plus 3 ones. 5 divided by 17 is 0.294 moles of NH3. That's the count. Then I have a 3 to 2 relationship between hydrogen gas and NH3. So for every 0.294 moles of NH3, I'll get 3 halves as many of hydrogen, and then I need to get to grams, so I multiply by the molar mass of hydrogen gas. This next set of mixed examples, I'm going to postpone because these are quite hard, actually. So let's go on to the limiting reactant section. Okay, limiting reactants, we are given amounts of both starting materials, and so we aren't sure which one to use to figure out how much product we'll get. It's unlikely that we'd have exactly the right amounts of both reactants. One of them will be abundant and one of them will be in short supply, and this will dictate how much product we get. So we have to first figure out which one is the limiting reactant. So this one we're given 10 grams of this. I like to write underneath the reactant, the amount, like this. I keep it neat, like this. Okay, so I have 8 grams of that and 10 grams of that. Don't be misled to think that hydrogen is the limiting reactant. No, we have to do it on a moles basis, the count basis. Well, these guys only have a molar mass of 2, so if I divide this by 2 grams per mole, I see that this is 4 moles. I have 4 moles of H2. And then N2 has a mass of 28 grams per mole. So this one ends up being 0.36 moles. So clearly N2 is the limiting reactant. Whoops, you know what I forgot to do is balance this first. So 3 of these with 1 of those combines to make 2 of these. So I do have to consider the fact that these get consumed 3 times faster than these. And so I would have a little over 1 mole of this. If I take 4 divided by 3, I could see in my mind I have more than a mole. Still, this is the limiting reactant. And what I like to do is star it and call it my LR. Okay, this is my limiting reactant. So this will dictate the amount of product. So use your coefficient bridge. My coefficient bridge here is a 2 to 1. 2 moles of NH3 to every 1 mole of N2. So I will get 2 times 0.36 or 0.72 moles of NH3. And then the molar mass is 17 grams of NH3 per mole. And you'll get 12 grams of NH3. 12 grams of NH3 will be produced. Okay, next problem. How much hydrogen gas is released when 5 grams of calcium, okay, here's that, 5 grams, is added to 10 grams of hydrochloric acid? This is 10. Now, I need to put a 2 here because this isn't balanced. Now it's balanced and I need to get to moles. So I take the 5, I divide by the molar mass of 40 grams per mole. And this will have, this will be 0.125 moles. The molar mass of HCl, I do not use the 2 here, okay? Please don't use the coefficient at this point. When you get to moles, you just take the 10 and divide by the molar mass of HCl, and that ends up being 0.27 moles. So we see this seems smaller. Do think about the fact that this gets consumed twice as fast, so you should really divide this by 2 to make your decision. But we still find that that would be 0.13, so this is still the LR. Okay, so this says use the calcium for the calculations, and we're just caring here about hydrogen gas. We don't care about the other product. What's your coefficient bridge on this one? You get 1 mole of H2 for every 1 mole of calcium, and so we'll produce 0.125 moles of H2, and then it's 2 grams per mole. So you would produce 0.25 grams of H2. I hope you're getting the hang of this. Let's do one more. I have to first write the reaction equation, and what we have here is chlorine gas, which is a diatomic, remember, will react with potassium iodide, which is Ki, and what you're going to find is the chlorine is more reactive, and it's going to pick up the potassium and do this. It's going to bump out the iodine in such a way. Alright, so now we have a balanced chemical reaction equation, and we are told that we have 23.4 grams of this and 51.2 grams of this. Okay, so we get to moles to be able to make a comparison. You can't look at grams and make a decision because atoms have different masses. We need to get to a common base of moles. Well, 2 chlorines is approximately 71 grams per mole. So that ends up being 0.33 moles. That's a 0.33 moles. Ki, iodine's pretty heavy. That turns out to be 166 grams per mole. And so we end up with 0.31 moles of that. So you have 0.33 and 0.31, but we do need to take into account the fact this disappears twice as fast. Every one of those combines with 2 of these. So in your mind, you could divide that by 2, and you could see that it's the Ki that will be disappearing quickly. So that will be our limiting reactant. So with that decision, we use that for the coefficient bridge, and we look at our relationship. We will produce 1 iodide, 1 mole of I2 for every 2 moles of Ki. So we will have 0.31 divided by 2, which is 0.15 moles of I2 are produced, and these heavy atoms that are 127 grams each, so it's 254 grams of I2 per mole of O2. I2, I should say. Yeah, that's 39.1 grams of I2. There we've gone through several stoichiometry examples, and stoichiometry is calculations with chemical reaction equations working with quantities. So our key thing was we can relate any 2 species within a chemical reaction equation through moles. The coefficients of a balanced chemical reaction equation give us that mole-to-mole relationship. If we are asked to go to grams, that's just an extra step at the beginning and at the end to convert from moles to grams or grams to moles. Hope that makes sense to you. Ask me if you have any questions. Thanks for your effort. Appreciate it. Bye.